In our previous lecture, we saw how one can obtain the controllable decomposition for a given LTI system. And in this lecture, we will make some important observations about this representation. Okay. This is an important theorem regarding this particular decomposition. For each system, okay, an LTI system, one x that equals ax plus bu, where the order of the system is n, and the size of the input vector is k, whose controllable subspace has dimension n bar. Okay, so this is necessarily less than or equal to n. Whenever it equals n, we say that the system is controllable. Okay, but for the general case, it doesn't have to be equal to n, so we expect that it's something smaller. There is a similarity transformation z equals t inverse x. T is n by n matrix. T is in Rn by n. That transforms the system the original system, into the following form, which we denote by equation number 2. Z dot equals A tilde Z plus B tilde U, okay, where A tilde and B tilde are of the following special form. A tilde, our new system matrix, is in upper block triangular form, and the matrices are labeled as follows: AC, A12, and AU. And as for the B tilde matrix, it has the following form: BC and 0. Now, as for the dimensions of these submatrices, AC is a square matrix of size n bar by n bar, and AU is a square matrix of size n minus n bar by n minus n bar. Okay, and BC is a matrix of size n bar by k. Okay, where AC is a square matrix of size n bar by n bar, and BC is of size n bar by k. Okay. Now, this is the first part of the statement of the theorem. We don't have to prove it because, in a sense, we already proved it in our previous lecture. We figured out that we can always find a t that puts the system in this form, and that t we saw that we can construct by letting it have the form V and U put together, two matrices, where both of those matrices have n rows, where the first part V is such that its columns make a basis for the controllable subspace, and the remaining n minus n bar columns of T are such that together with V and U, they make a basis for the entire space Rn. Okay, so U is in that sense arbitrary. And if you use such a transformation where the first n bar columns make a basis for the controllable subspace. Under that transformation, the new system that you obtain has this very special structure, okay, where the A tilde matrix is upper block triangular and the B tilde matrix is such that below a certain line all its rows are 0. Okay, now this representation has some further properties, so let's continue our theorem, for which the following holds: A, the controllable subspace of the transformed system, that is system 2, is as controllable, okay, tilde range space of this matrix n bar by n bar 0. Okay, now since this is the controllable subspace of a system of order n, okay, the column vectors of this matrix must be vectors in Rn. Okay, and since here we have identity matrix n bar by n bar, it means that this matrix has n bar columns. Okay, and then it says that the first and the matrix is such that the last n minus n bar rows are all 0, and the range of, or the range space of this matrix is the controllable subspace of our transformed system. Furthermore, okay, and B, the pair AC BC, okay, is a controllable pair, is controllable. Okay, so let's prove this theorem, and as we just mentioned, the first part is already proven in our previous lecture, in the first part being that there exists a transformation such that this system is or can be put in this new representation. Okay, now let's therefore prove the remaining pieces. So let us form the controllability matrix for the system 2. Okay, so this is our system 2. This is A tilde, this is B tilde, so the controllable matrix is B tilde, and then A tilde, B tilde, then A tilde squared B tilde, and so on. So you put all those columns side by side, make a big matrix, and that big matrix, which is of size n by nk, is your controllable matrix for the system 2. Now, because of the very special structure of A tilde and B tilde matrices, the controllable matrix will also have a special structure. So let's discover what that structure is. We're calling the controllable matrix of the new system, system 2, by C tilde. C tilde is, okay, by definition of controllable matrix, we have B tilde. Okay, let's call it A tilde, and let's call it B tilde. And then we have A tilde, B tilde, which is AC 0, A12, AU times B tilde. You keep doing that until the n minus first power of A. AC A12 0 AU raised to the n minus first power times BC 0 B tilde. Okay, and this is your controllable matrix for the controllable decomposition. Now, because of the special structure of these matrices, what we have here is AC. So this matrix produces the following columns: AC times the first entry is AC BC plus A120. Therefore, we have AC BC. Okay, and for the second part, we have 0 times BC plus AU times 0, which is 0. So therefore, this equals AC BC and 0 matrix. Okay, and then you go to the second term where you have this matrix square times BC0. Now, because this matrix has upper block triangular form, its powers also inherit that property. Okay, for instance, the n minus first power of this matrix is AC n minus 1, AU n minus 1. Okay, and here we have, okay, here we have 0, and here we have I don't know what. Okay, now, nice thing about my not knowing this this entry is because we don't need that entry when we're performing this product. Okay, so what we have is, because that entry is multiplied by 0, so what we have here is AC n minus 1 times BC plus this star don't care times 0, so that produces AC raised to the power n minus 1 times BC. As for the bottom part, it's 0 times BC plus this matrix times 0, so that produces 0. So in other words, what we have is, this whole thing can be written as BC 0, and then we have AC BC 0, AC square BC 0, and so on, AC n minus 1 BC 0. Okay, so that's the controllable matrix of the transform system. Note that it has a very special structure, which is that the last n minus n bar rows are all 0. Okay. Okay, so this form immediately tells us that, or puts an upper bound on the dimension of the controllable subspace. Okay. Furthermore, we can say that range space of the controllable matrix C tilde must necessarily be a subset of range space of this matrix. Okay. Okay. Since the less n minus n bar rows are all 0, any linear combination of the columns, okay, of this controllable matrix would yield a vector that has the form some entries for the first n bar, some numbers for arbitrary numbers for the first n bar entries, and the remaining n minus n bar entries, it will be all 0 because of this structure. Hence, the range space or C bar, or the subspace that's spanned by the columns of the controllable matrix, must necessarily be a part of, or the subset of, the range space of this matrix, where we have the identity here and the remaining rows are 0. Now, the dimension of this subspace clearly is n bar, because this matrix has n bar many linearly independent columns. So that makes that the rank of this matrix is n bar, hence the dimension of the range space of this matrix is also n bar. So we have dimension equals n bar. And how about the dimension of this matrix? Well, since this dimension of this subspace, since this subspace is a subset of this subspace, okay, the dimension of this subspace can be at most n bar. Okay, now let's try to be more precise about that number. Okay, so let's call this relation 3. Furthermore, we have the dimension of the range space of the controllability matrix C bar equals dimension of the range space of T inverse times the controllability matrix of the original system. Okay, so C is B, AB, A, N minus 1B. Okay, so that's controllability matrix, controllability matrix of the original system, original representation. The reason is that C tilde equals T inverse times C. So that relation we also derived in our previous lecture. And then this by definition is rank of this matrix T inverse C. Since T inverse is a non-singular matrix, the rank of this matrix and the rank of C must be equal. So that equals rank of C. And by definition, rank of C is the dimension of the controllable subspace, because range space of C is the controllable subspace. So this equals n bar. So that's our equation 4. Now let's combine relation 3 and with equation 4. Here we have the following subset relation, and we have just figured that the dimension of this subspace must be n bar. So this, we have two subspaces. One is a subset of the other, okay, and both have the same dimension. That's only possible if both those subspaces are equal. Okay, so combining 3 and 4 therefore yields that the controllable subspace of the transformed system must equal the range space of identity matrix here and 0 here. Okay, so that proves part A. As for part B, we can argue as follows: n bar equals rank of n bar equals rank of C bar, because rank of C bar, C tilde is by the definition dimension of the range space of C tilde. Okay, and rank of C bar equals C tilde. C tilde is here. Now, since the less n minus n bar rows are all 0, the rank of this matrix clearly equals the rank of its upper part. Okay, because these zeros will have no contribution to the rank. So we can write BC, AC, BC, AC n minus 1, BC. Okay, now remember that AC is an n bar by n bar matrix. Okay, so by Cayley-Hamilton theorem, any power of AC which equals n bar or larger can be written as a linear combination of the powers of AC starting from the 0th power to n bar minus first power. Okay, so that means starting from n bar, the terms n bar AC to the n bar times BC, AC to the n bar plus 1 times BC, those columns will not, they have to be linearly dependent to the columns previous, coming before them, okay, due to Cayley-Hamilton theorem. In other words, the rank of this matrix, or, okay, let's forget about rank, the range space of this matrix, okay, or the subspace spanned by the columns of this matrix equals the subspace spanned by the columns of this thinner matrix. Thinner in the sense that we don't go as far as n minus first power, but we stop at the n bar minus first power. N bar minus first BC, okay. because n bar is less than n, so this matrix is necessarily a thinner matrix. And since they both span the same subspace, by definition they must have the same rank. And this step is by Cayley-Hamilton theorem. Okay, and then the rank of this matrix, if it's n bar, therefore considering this as the controllability matrix of the pair AC-BC, we see that by definition of controllability, or one of our controllability theorems, the pair AC-BC must be controllable. Okay. The pair, therefore, AC-BC must be controllable, which completes the proof of our theorem about controllable decomposition. Okay. Now, in the second part of our lecture, we will study the relation of the controllable decomposition to the transfer function of the original system. Okay. So for that, or to see that easily, let's move on to the block diagram representation of the controllable decomposition. Okay, so block diagram interpretation. Okay, so once again, what we have done is we start with a system, okay, x dot equals ax plus bu. Now we will be talking about the transfer function, therefore we have to also introduce the y part, cx plus du. Okay, and then by controllable decomposition, okay, by a suitable choice of similarity transformation, where the first n bar columns make a basis for the controllable subspace of this system, and n bar being the dimension of the controllable subspace, we have obtained the following form. Okay, z dot equals plus u, I have to squeeze certain things, and y equals c z's times z plus du. Okay, now this will be c tilde, this will be ra tilde, this is r b tilde, and d tilde and d, they are the same for both systems. Now a tilde we know is of the following form: AC A120 AU. AC is an n bar by n bar matrix, n bar being the dimension of the controllable subspace, and b tilde has this form BC0, where this the second part where we have all zeros is such that we have n minus n bar 0 rows, okay, for the second part. Okay, and then what we do now is, this is RZ dot and that's RZ. We write Z as a vector that has two pieces, okay? Part ZC and part ZU. ZC is of appropriate dimensions such that AC times ZC is meaningful, okay? ZC, this is ZU. Here we have the dot. ZC, ZU, okay? So since AC is n bar by n bar, so this matrix, the Z matrix, is such that its first component ZC is a vector in n bar, Rn bar, and the second component is a vector of size n minus n bar. Okay, so A is n by n. Okay, and after the transformation, let's call the pieces of C tilde as CC and CU. Okay, so after having written in that partition form the controllable decomposition where A tilde is T inverse AT, B tilde is T inverse B, and C tilde is C times T, and D tilde equals D. Okay, we can now start talking about the block diagram representation, and then from there it's easier to make certain conclusions regarding the transfer function of the system. Okay. Block diagram for the controllable decomposition. Now, the very important thing that we will be using at this point is the fact that since these two systems, they are algebraically equivalent, okay, they produce the same transfer function. Therefore, in order to study the transfer function of this system, we can always use the transfer function. We can always use this state space representation because it will produce the same transfer function. Okay. Now, what's the block diagram for the controllable decomposition? So we have two, let's say, sub-dynamics of the overall dynamics. One is the dynamics due to this substate ZC. The other is the dynamics due to the substate ZU. Okay, so therefore let's represent them as two blocks, two separate blocks. Okay, this is our ZC dot equals AC ZC plus the other terms. Okay. This is the input to the system, and what the system produces is ZC. And let's do the same thing for the second subdynamics. Okay, ZU dot equals AU ZU plus the other terms which we represent by W. Okay, so this here is W, and this guy produces ZU as its output. Okay, and now let's, using those blocks, pave the path from the input to the output. Why? Because we want to obtain the transfer function, and transfer function studies the relation from the input to the output. Okay, so what's V? Okay, for the ZC dynamics, so ZC dot equals AC ZC plus A12 ZU, okay, plus BC times U. Therefore, this V, okay, that part which we consider as the input to this block is A12 ZU plus BC times U. So here let's put some summer block here plus, okay, so we need BC times U here. Okay. Let this be the gain block. Gain, but gain in the general sense. So these blocks are represented by matrices. And BC, and here we have the input U. Now, the output of this block is BC times its input, BC times U. Okay? So ZC that equals AC ZC plus A12 ZU plus BCU. Now, if we have BCU, we also need A12 times ZU term. Therefore, let's put another gain block here. It's A12. What it produces is it takes ZU as its input, and at the output we have A12 times ZU. So A12 times ZU plus BCU, okay, produces our extra terms, which we denote by V. Okay. Now, the ZC dot dynamics are now complete. How about the ZU dynamics? ZU dot equals AU times ZU. Okay, and that's it. Because here we have 0, the input does not directly affect AU, and here we have 0, therefore ZC dynamics cannot affect ZU dynamics too. Therefore ZU dynamics, in a sense, they are independent from the rest of the circuit. So we have here 0 for the W. In other words, ZU dot equals AU ZU. The only thing that determines the evolution of ZU, therefore, is the initial ZU, initial conditions, ZU 0. Okay. Now, the dynamics are complete, ZC and ZU dynamics. Now, let's figure out the output from those dynamics. What's output? Output equals CC ZC plus CU ZU plus DU. So output is the sum of 3 terms. Okay. So one of them is here. The other is here. Okay. And then we have yet another here. Okay. And then what we do is we sum all those signals to produce our output. Okay, this is our Y. Okay, so here this is the term coming from ZU, therefore that gain block should be CU. Here we have the term coming from ZC, okay, so that gain block should be CC, and also we have the term coming from the input, so that block is D. Okay, so let's connect a line from the input. Okay, and now our block diagram is complete. Okay, we have the ZC dynamic, we have the ZU dynamic, and we have the output as a summation of 3 pieces. The piece directly coming from the input, the piece coming from ZC dynamics, and the piece coming from ZU dynamics. Okay. Now, whatever the transfer function that we obtain from this block, from input to output, is the transfer function of this controllable decomposition, which is algebraically equivalent to the original system. Therefore, the transfer function coming from this block diagram must be the transfer function of the original system. So let's see what we can say about the transfer function of the original system then. Okay, we have to remember something about the transfer function. Transfer function is the ratio of, okay, for simplicity's consider the scalar case. If in general it's a transfer function matrix, but consider the general simple case, it's the ratio of the Laplace transform of the output to Laplace transform of the input, under the assumption that all the initial conditions in the system are 0. Okay. So ZC 0 is 0 and ZU 0 is 0. Now, if all the initial conditions are 0, that means ZU 0 is 0, okay, time t equals 0. Now, the input to this block is 0, and the initial condition is 0, therefore it will remain at 0 for all times, okay? So this signal from the transfer function point of view, therefore, is always 0. Therefore, this signal here is 0, and also this signal here is 0. In other words, we can just ignore the part of this block diagram below this dashed line, and nothing will be lost from the transfer function point of view. Okay, in other words, we can work with the simpler block diagram. So note that to obtain the transfer function, GS, where YS equals GS times US, we assume 0 initial conditions. Okay, which implies that as far as we are only concerned with the transfer function, all we need to consider is the below block diagram. Okay, I will just, for sake of completeness, I will redraw the upper part once again. So here we have, therefore, okay, so this is BC, this is ZC dot equals AC ZC plus BC U. Okay, well, let me put it plus V. Here we have the D matrix, here we have the CC matrix. Okay, so let's now figure out the state space representation of this simpler system. So this block diagram yields the following representation. ZC dot equals AC ZC plus BCU, and Y equals CC ZC plus DU. Okay, so this is a simpler, in fact, a system in general of degree smaller than the original system. And this produces that the transfer function corresponding to the system equals SI minus AC inverse BC plus D. Okay, so what we have obtained is the following. We start with some system, okay, general system, x equals ax plus bu, y equals cx plus du. We put that system into the controllable decomposition and obtained A tilde, B tilde, C tilde, and D matrices. Now, since those two representations are algebraically equivalent, they must have, we know, the same transfer functions. Okay, so this is the block diagram representation of the controllable decomposition, and we wanted to obtain its transfer function, which would be the transfer function of the original system. And because of the spatial structure of the controllable decomposition, and because that when we talk about the transfer function, by assumption all the initial conditions are 0, we saw that this part, which can be called the uncontrollable part, has no effect on the output. Okay? In other words, has no effect on the transfer function, and it can be ignored. So that's what we did. We ignored it and obtained this simpler, smaller system, and this system has this transfer function. Okay, and this transfer function, okay, must be the transfer function of the original system. In other words, the transfer function of the original system equals the transfer function of its, in quotes, controllable part. Okay, so let's put that conclusion down and we can end the lecture. So the conclusion is the following. The transfer function of the original system ax plus bu y equals cx plus du equals the transfer function of the smaller system, which we call the controllable part of the controllable decomposition of its controllable part, okay, which can be represented by the quadruple AC, BC, CC, and the matrix